generally different types of functions. So at this point in your mathematical career, you should be able to picture what a graph looks like just by looking at its equation, more or less, a general idea of that. So we're going to run through what I'm going to call the parent functions first. And these are just going to be like general types of equations that you need to see. Some of them, pretty much all of them, should be ones that you have seen before. So the first is the constant function. Okay, and the parent function is the line y equals 0. And we need to draw this in because it is graphed here, but you really can't see it because it is just the x-axis. So you probably need to draw it in there because I graphed it, but it didn't really show up because it was on top of the axis. I think I made this worksheet pre-Desmos. I can't remember what it was I was using now. I think that's Desmos. It didn't show up very well. It didn't do colors. Yeah, it wouldn't have printed it anyway, but it would have shown color here, so I must not have had colors, I guess. So constant function is a horizontal line. You basically can only move it up or down. There's not much else you can do to it. I'm going to just skip over here just because it's easier to do. The next one we see right here is y equals x squared. This is a quadratic function. The word parabola could also be used. The word parabola only applies to the graph. So that is a graph of a parabola, but the function, the equation itself, you would call a quadratic. So parabola refers to the graph there. So we would call the function a quadratic, and the parent function is just y equals x squared. It is going to look like this, the sort of U shape. There's a lot of things we can do to transform it. You should be pretty familiar with this one. We started in Math 1. This function here has a slanted line. We call these linear. Now, technically, the constant graph is also linear, right? Because it is a straight line. But it is a very specific type of straight line that is horizontal, right? So you technically could call that constant graph linear, but you can't call this graph right here constant. So it's sort of like a square is also a rectangle, but not all rectangles are squares. The parent function for this would just be the line y equals x, which is just a line with a slope of 1 and a y-intercept of 0. Lines should be very familiar to you. We'll talk about them more here towards the end. This graph right here is a cubic function. So your parent graph for that is y equals x cubed. The next one right here is a square root. You will occasionally see this called radical. Although radical is a more broad term because radicals include square roots, but they could also be cube roots and fourth roots and fifth roots and sixth roots and whatnot. So the most specific name for this would be a square root function. And the parent for that is just y equals square root of x. Next to it here, we've got this V shape. What is that V shape? Absolute value. This one is one that you focus on in Math 3 a lot. You do some solving absolute value functions and look at that one a little bit more. We'll see it, but it won't be our main focus. Next, we have 1 over x. This is a rational. function. And in order for this to be rational, the variable is in the denominator. Sometimes you'll see equations like this, x divided by 2. That is not rational, because your variable is in the numerator for that. And then the last two types of graphs we've already talked about quite a bit in the last unit because they were the focus of our last unit. The last one is logarithmic. This particular parent function, I use natural log, but really it could be whatever log with whatever base. So it could be the common log, or it could be log base 7. It's just log of the x there that you have there. And then our last one here is exponential. And I use the parent function of y equals e to the x because it's one we're going to use very frequently, but it could be 2 to the x or 7 to the x or 10 to the x there. So one thing that you need to be able to do is be able to match this general shape of the graph with the type of equation that you're looking at. So we are going to have a quiz. I think it's Friday. No, it's not Friday. Y'all are not here Friday. I think it's Thursday. I think. Let's see if that looks right. Yes. On Thursday, we are going to have a quiz. I will tell you right now, one of those questions is going to be a matching question. And it's going to have, like, however many we got here. 1, 2, 3, 4, 5, 6, 7, 8, 9 graphs, and it's going to have 9 words, right? And you're just going to have to match the constant graph to constant and quadratic to quadratic, right? So you're just going to have a picture of a graph, and you got to tell me what it is. So being able to recognize, just looking at something, oh, that is a quadratic. That is important for us to know. Most of these look a lot different, so they're pretty easy to tell apart. Sometimes the logarithmic and exponential can look a little the same, but I won't give you anything that's been transformed crazy. It'll still look like logarithmic or exponential there. So you'll need to be able to recognize those. One thing, so our main focus beyond that is that we need to know how to transform these graphs. So you should have worked on this some already. What I think is so cool about this is it does not matter which graph you start with, they all behave the same. So it doesn't matter whether or not I've got an exponential or a linear function or a quadratic. If I do any of these things to them, it's going to have the same effect on the graph, which is pretty cool. And what we're going to see is we're going to take this even further, because part of the stuff that we have to look at is trig, and we're going to see where trig graphs react the same way, right? So on trig graphs, if we put a negative out front, it still flips it upside down. So the longer I have taught, I think whenever I was in school, I did not understand like the importance of this as far as being really good at math. But the longer I have taught, the more I understand the importance of this, because it gives you a picture of what the graph looks like in your mind without you actually having to graph it. Now in Math 3, you can use Desmos on everything, so your mind doesn't need to know what a graph looks like, because Desmos just tells you what the graph looks like. It does an excellent job of that, right? So, and there's times whenever that definitely is something that we want to know. But understanding mathematics, knowing what happens to this, just helps you understand like what a problem is asking so much better. It will make you be able to answer questions a lot more quickly than having to go to Desmos. Like, for example, ACT questions. If you know that if I add 7 to the end, it's going to move the graph up 7, I don't have to go graph all those answer choices in Desmos. I just see, oh, there's a +7, it's that one, right? It went from being something that's going to take you a minute and a half to do to something that takes you 10 seconds to do. So it just really helps you in your overall understanding. So the rules that we're going to see. And I'm going, for these, I'm going to do an example for all of these with a parent function that is a quadratic, y equals x squared. All right? So, and I'm even going to pull up, I mean, Desmos is helpful, don't get me wrong. I don't mean to be hating on Desmos because it's wonderful. But it's good to know how to use it and how to do it without it as well. So, like if I graph f of x equals x squared. All right, there's this. So if I make the entire function negative, this is what it's going to look like. Y equals negative x squared. Okay, so if I go over here and I do, actually I think it will let me do negative f of x. All right, oops. Negative f of x. No, type it in right. Okay, this is really cool because I can change my function if I want. So I'm going to do it this way. But if I just put a negative in front of my x squared, what does it do to my graph? Flips it upside down. Specifically, using fancy math language, it reflects over the x-axis. Right, that would be your most refined mathematical language there. Okay, so that is helpful. So if we see a negative out front of an entire equation, it's just going to flip that equation upside down. It doesn't matter what the function is. So like, for example, let's say I didn't have x squared. Let's say I had 2x squared plus 3x minus 7. It still just took that red graph and flipped it upside down, right? If I had something like square root of x plus 7, let me put a plus 3 on the end so you can see it. If I have the square root graph, which is this red graph, if I put a negative out front, which would be like a negative and then a parentheses around all that stuff, it's just going to flip it upside down. So, x squared, though, is what I want to stick to looking at. So, flex over the x-axis. Now, there's a difference in the first rule and the second rule. Okay? The second rule does not put the negative out front. It puts the negative inside of the parentheses. So for y equals x squared, it would look like this. Negative x, and then the square would be out here. All right, so let me try doing that over here. I'm going to take that negative, I'm going to put it on the inside. Uh-oh. There's my red graph. There's my blue graph. It didn't do anything. But I feel like Ms. Hyatt would not have listed this here if it didn't do something. So it should be doing it right, but like if I want to type it in this way instead, negative x squared, still same thing. Okay, so what's happening is it is doing something. That is doing something to the graph. But because of what this graph looks like, we can't tell what it's done. Okay, let's try something else. Let's make this x to the third. Let me get rid of this one. Okay, so now look at my red graph versus my blue graph. It reflected it across the y-axis. Why didn't it look like it did anything whenever I had the x squared? It's symmetric, right? The two sides look the same, so it didn't look like it did anything, but it actually was reflecting it over the y-axis. So negatives on the inside of the parentheses are going to reflect over the y-axis. And as we just showed with x squared, for some functions that doesn't look like it did anything. The absolute value is going to be the same way. If you put the absolute value inside of that negative, it doesn't look like it does anything because it is symmetrical about that y-axis. But for other functions, it makes a difference. Okay? All right. So The next one is the f of x plus c. This one should be most familiar to you. It would be something like x squared plus 5. What's going to happen if I put a plus 5 on the end of that? Up 5. So up, I'm going to put c units. Actually, let me revise that. Let me not say just up. If I put plus 5, it will go up. But what if I put minus 5? It'll go down. So it's going to go up or down c units. And it's going to go in the direction you think it would. So, like if I put plus 3 here, it's going to move the graph up 3. Or I guess I put 5. Right there. If I put plus 5, it'll move it up 5. If I put minus 2, it moves the graph down 2. Right? So, so it just goes the direction that you think it would go. All right, who can remember what happens when we put the plus c on the inside of the parentheses? It's going to go left or right. So if we're adding or subtracting, it's still going to go, it's what we call a translation. You're just sliding it. It's going to go left or right, c units. But let's try it here. Like this would look like this if I'm doing y equals x plus 2 squared. So let's say I put a plus 2 right there. Okay, which direction did that plus 2 move my graph? Red was my original. It moved it to the left. But I put a plus 2, right? That is the positive direction, which would make me think the right direction, right? So what I tell students often, everything inside of the parentheses is backwards. Right, so like this negative right here on the outside flips it over the x-axis, but if we put it on the inside, it's backwards. It flips over the y-axis. So if I add a number here, it's going to move it up. But if I add a number on the inside, everything's backwards, right? So I put a plus 2, it actually moved it left 2. So I'm going to put opposite direction here. So if I want to move something to the left 8, I would need to put a plus 8 for that. If I want to move something to the right 2, I would need to put a minus 2. So adding or subtracting, either inside or outside of the parentheses, that is going to move your graph up and down or left or right. Now let's look at what happens whenever we multiply. This is going to be a little bit different. So I've split this y equals c times f of x into 2 separate sections because we're going to see different things happen here. So this would be, for example, something like y equals here where my c is greater than 1. So it might be something like y equals 2 times x squared. Okay, not inside the parentheses, it's out front. 2 times x squared. So if I just put a 2 right here. Okay? So if I look at my graph, these are a little harder to picture what is happening, right? So red was my original. The blue, what could we say about it? Okay? It's going to be stretched vertically. It also looks like it's squished horizontally. So sometimes it's hard to tell which one you're looking at. But we can tell by where our numbers are at. So if our number is on the outside, over here, like this, it's not inside the parentheses, it's going to be a vertical. I'm going to use the word expansion, but the word stretch is also sometimes used. It just depends on what worksheet or textbook or test you're looking at. So I'll try, I typically on my worksheets are going to use, in my like tests and stuff, are going to use the word expansion and compression more often. but stretch and shrink, like I have seen textbooks with those terms in them before, so I may use both there. And so what we're thinking about is like we're thinking about grabbing that y-axis and stretching it. So think about what would happen, like if we took someone and we stretched, like they stayed the same weight, right? Their mass is the same, but we took them and we just stretched them taller, right? What would happen to that person? They would obviously be taller, but they would also probably look skinnier, right? Because their mass is the same, but they've been stretched out taller, right? So that's kind of what happens to the graph right here. You're stretching it taller, which also makes it look skinnier. But if we put a number between 0 and 1, something like this, like y equals 1/2 x squared. So if I put 1/2 right there. Now, red is still my original graph. What has happened to this graph? It now has been squashed to make it shorter, although what's going to happen, right, if you take me and you squash me down and I'm only 5 foot tall, but my weight, my mass does not change, I'm going to look a lot wider than I look right now, right? So you're mathematically vertically, that's what's happening, but it also makes it look wider, right? So this is a vertical compression or shrink. Okay, now from the graphs, these are a little bit difficult because we're getting ready to do this. We're going to do the same thing right here, but we're going to put it inside of the parentheses. So instead of having 2x squared, we're going to have parentheses 2x squared. All right, so we're putting that 2 inside of the parentheses. So it's going right there. Now, if I look at this graph, the red right here is still my original. It looks a whole lot like what happened when I multiplied it by 2, right? It looks like it stretched it out. But that's not actually what's happening here, okay? What's happening here, because that number is on the inside, it is a horizontal compression, okay? So you're squishing it that way. But if I take someone and their mass is not changing, I squish them in this way, it's going to have to make them taller. Right, so it looks the same. In fact, we could write vertical compressions or vertical expansions that are the same as our horizontal compressions. Like they would give us the same result. So this is going to be horizontal, and it's going to be a compression or a shrink. Now, here's something I want you to note. Out here, when I multiplied by what I'm going to call a big number. When I say big number, I just mean bigger than 1. That's not a mathematical term. This is just to help you remember it, right? I multiplied by a big number. It was a vertical expansion. But look what's happened here. I multiplied by a big number, a number bigger than 1. And what did it cause? A compression, right? So just like up here with when we were talking horizontally, when we were looking inside of the parentheses, everything's backwards, right? So adding 2 actually makes it move left 2. Multiplying by a big number is actually going to be a compression, right? So you always see those kind of backwards there when we're inside the parentheses. So what do you guys think is going to happen if I put a 1/2 inside of the parentheses there? is going to be horizontal expansion. And if we look at it there, here we've got horizontal expansion, or we could call it a stretch there. Again, we're thinking horizontally. We're taking the x-axis and we're stretching it out this way, right? Which is going to make that graph look wider. Okay, we'll talk a little bit more about this, but the expansions and compressions are usually the tricky part. Those are a little tricky. The last one I want to look at, we're not going to do a ton with this, but I just think it's cool and I want you to see it, is taking the absolute value of a function. Okay, so I'm not talking about the V graph. I'm not talking about starting with the V graph, although you could have an absolute value of an absolute value. But I'm just talking about any function. And if I take the absolute value of it, so that would look like this. Like if I had y equals, and I'd be doing the absolute value of x squared. Okay, although we're going to see x squared doesn't give us a whole lot there. So in Desmos, I think there is a feature for this, but if you just type ABS, that is absolute value. But here's an example where the function x squared does not give us a lot because nothing happened to it, right? However, you can imagine that I'm giving it to you for a reason, right? So it probably does something to some functions. So I'm just going to give you a few different functions. I'm going to change this right here to make this function minus 7. Okay, so red graph is my original right here. Here's the blue graph. Oh, wait, that made it go away. There's the blue graph. Okay, let me change this original function. Let me make it square root of x minus 4. Okay, let me go over here. Okay, the red is my original. The blue is my absolute value of that function. Well, it's not exactly just like just flipping it upside down, right? But parts of it are flipping upside down. So let's try and let's do another one. Let's do x to the third. That's a good one to do. So here is x to the third cubic. That's the original, right? That's what the cubic function looks like. That red right there. Oops. There's my original. Here's what the blue looks like. Let's do one like x to the second minus 8. Actually, I'm going to do like x plus 2 minus 8. Okay, here's my original, my red function. Here's my blue. So, can anybody put into words what's happening there? What's... Yes. Yeah. So it follows this. It's just the same graph for most of the graph, right? So like right here, the red graph and the blue graph are the same till you get right here. But right here, it's trying to go negative. But what's the absolute value saying? Nope, you can't be negative because I am here and I'm going to wash away all of the negatives, right? So what we see is this part of the graph gets sort of like bounced back up to the positive part because the absolute value is washing away all the negatives here. But then once I get back to the point where our original graph was positive, then I'm just following that graph again, right? So this one is just kind of a weird one that I like to look at. So it's going to reflect the negative parts of the graph over the x-axis. But it leaves the positive parts alone, right? Because with absolute value, everything would be positive. So why did it not work for x squared? X squared just looked normal. It is never negative there, right? So it doesn't have anything to flip over the x-axis because there are no negatives. Right, so if we put a -4 right here, look what happens. There now my original does have a negative portion. So on my blue graph where I'm taking the absolute value of it, it flips that middle part up. It's almost like it turns it inside out, just those negative parts, right? The first ones are really, really, really important that we know them really well. This one's just kind of cool, and I wanted you to see what would happen to it. Although it does have some application because there are some things like that can't be negative, so you might have to consider it. Okay? All right, so, all right, this is just a reminder, and kind of what I was saying about the inside versus outside. When a number is inside of the parentheses, either x plus c or c times x, the graph will behave in an opposite manner than you think it should. For example, a positive number added to the x will make the graph move in the negative or left direction. And a larger coefficient in front of the x will result in a horizontal compression while a smaller coefficient, something between 0 and 1, will result in a horizontal expansion. Okay, and then I just have this visual here. If we're thinking about a vertical expansion, it's like you're taking that y-axis and you're stretching it out like that, making it taller. A vertical compression, you're squishing it in like that. Horizontal expansion, you're stretching it out, makes it wider. Horizontal compression, you're squishing it inward, makes it skinnier. There. For that. One thing we're going to have to be able to tell about these is the factor that they are compressed or expanded by. So, for vertical expansions or compressions where we have a times f of x, so the number is here on the outside of the equation. We would say that f is expanded or compressed vertically by a factor of a. It's just going to be whatever that number is. But if we have that number on the inside, right? If we have that number on the inside, then it's going to be a horizontal expansion or compression, and it's going to be expanded or compressed by a factor of 1 over a, 1 over whatever that number is. So much like what I was saying before, if the number's on the outside, you just use that number. It is what it is. If it's on the inside, everything's backwards. Everything's flipped. It's the opposite of what you would expect. So you got to do 1 over a for that. All right, so we're going to run through these examples real quick and look at the what we have, and then hopefully we'll have time to get started on your assignment. So, so we've got to tell the parent graph and then tell how it relates to the parent graphs and the transformations that have happened. So, for example, on this first one, we've got a quadratic. And quadratic would just be y equals x squared. So we're looking at all the things that are not just x squared, and we're trying to tell what has happened to the graph. So we got this plus 3 right here, and we've got this minus 2 there. When you're adding or subtracting anything, that's just moving the graph either up or down or left or right. It's sliding the graph. It's called a translation. So that minus 2 just means that we're going to move down 2, and our plus 3 means that we're going to move to the left 3. Because remember, anything inside of the parentheses is going to go the opposite direction. Plus makes you think right, but it really is going to be left. Okay, questions? All right, Abby, what is our parent graph for number 2? Good. So cubic, and a cubic is y equals x cubed is our parent graph. So the only thing that I have different here is I've got that 3 right there that is being multiplied by my x. So Troy, what do you think? What's that going to do?
Horizontal shrink.
Good. Horizontal. I'm going to use the word compression, but shrink is also okay. So horizontal compression, and I want to tell the factor. So by a factor of, and so we know it's horizontal because it's on the inside. It is a compression because we're multiplying by a big number, something bigger than 1, which is going to do the opposite. It's going to make it smaller. It's going to compress it. And so the factor is also kind of flipped there. So the factor is going to be 1/3. Because you're going to have 1 over whatever that number is. Okay. All right, Liam, what is my parent function for number 3? Good? Okay, so just the square root of x would be the parent function for that. Smith, give me one thing that has happened to that graph. Very good. So this negative right here that's in front of that is going to flip this upside down. So reflected over the x-axis. All right, Connor, can you give me something else that has happened to this graph? Is not left 5. This one's a little tricky in the way they gave it to you. Left or right has to be on the inside of the parentheses. Square roots don't have parentheses here, but where is it understood that the parentheses would be? Inside of the square root. So it's like you got parentheses right here. So I've got that plus 3 is on the inside of the parentheses, which is going to move the graph to the left 3. What's the 5 do? It's not going to shrink or compress. It's going to move it up 5. All right, the reason it does not shrink or compress, it looks like it should shrink or compress, but is that 5 times the square root? Are we multiplying? We are not. So the best way to think about this is we could write this equation this way, negative square root of x plus 3, and we could make this a plus 5 over here on the end. That is what we would more typically see, and I don't think it would confuse us as much if we saw it written there on the end. But that 5 is not multiplied, so it can kind of be brought to the back. right there. So it would move it up 5. If we had it looking like this, negative 5 square root of x plus 3, like that, that would be a vertical expansion or compression. Okay? Questions so far? All right. 4, this is going to be cubic. Let's see, Kendall, tell me one thing that's going to happen to that cubic. Oh. Is it inside the parentheses? It is not. So the parentheses would just be like right there around that x. So it would have to look like this, x minus 4 to the third power to move it to the right. So since it's not inside of parentheses, what's going to happen? Down 4. Good. All right, and Sophie, what does that 2 do to the graph? Vertical expansion by a factor of 2. Yeah, it's going to stretch it. It's going to take that y-axis and stretch it taller. And Sophie, how did you know it was vertical instead of horizontal? Right. It's outside of any type of parentheses there. Okay. When things are on the outside of the parentheses, a big number is going to make the graph bigger. Right? So it expands, and a small number will make it smaller. It compresses. Whenever it's on the inside of the parentheses, that's when that gets flipped. Big numbers make it smaller, small numbers make it bigger. Okay, 5 is tricky because this is rational, which means that you've got y equals 1 over x as your parent graph. So rationals do not have parentheses, but you could put parentheses in the denominator. So what is that plus 2 going to do to the graph? Left 2. What about that 3 on the top? It is like it's multiplying, because you can think of it like this. It's like having, I could write this way, 3 times 1 over x plus 2. Right? Because that would be like 3 over 1. I would just multiply straight across to multiply it back. I'd get 3 over x plus 2 if I did that. So when it's in the numerator there, it is like it's being multiplied. So if you are multiplying on the outside of the parentheses, what would we have, Monica? Vertical expansion by a factor of 3. So that numerator is really like the number you're multiplying by. There. Okay. 6, we've got a square root. I'm going to run through these last a little quick because I want you to at least pull up and look at the second part of the homework. So, square root, when you have a negative and a number being multiplied here together, you treat them separately. The negative is going to reflect over the x-axis. The 1/2 is a vertical expansion or compression? Compression by 1/2. And then this one is also going to go to the right. 4. So negatives are treated separately from the number. So if you have a -7, the negative flips, the 7 compresses or expands, right? Okay, these last couple, for 7, we're going to have an absolute value. Okay, I've got a 1/3. It's on the outside of the parentheses. The absolute value bars act like parentheses here, right? So, so it's going to be a vertical compression by a factor of 1/3. And then I also have that +5 outside on the end. That's going to be up 5. Okay. Questions so far? All right, last one's a little bit tricky. You got a square root. That negative out front is going to reflect over the x-axis. All right, I've got the 0.25. It's on the inside. What's that tell me? Horizontal, almost. Expansion. Everything on the inside is backwards. So small numbers make it bigger, so it's expansion. Which is confusing, and this is the one I always mess up, if I'm going to mess one up. Now, what factor? It's not going to be 1/4, because 0.25 does equal 1/4, right? So we got to do 1/1/4, which just flips it, right? Because dividing fractions is easy as pie. Flip the second and multiply, so it ends up just being 4. So you can see why that one's kind of the hardest of them. Okay, so your assignment tonight is going to be on Desmos Classroom. So you are going to see it's this functions card sort right here. So I just want to show you how it works. I want you to try your very, very, very best to do this without graphing these on Desmos. If you become desperate and must graph them on Desmos, you can. But I want you to try to do it without graphing on Desmos. So, you are going to match just the equations to the graph. Some of them, like this first one, you're mostly going to do it just on the shape of the graph. Like I know this is constant, so I'm looking for the graph that is, constant. So that matches to this one. And then I'm going to do, this one's linear, so it needs to be the equation of a line. That's that one. That one's rational. That one's cubic. I'm just doing this super fast. Exponential. Square root, logarithm. Those are different types of graphs, so I'm just basing it on the shape. You will go to the next slide, and it will tell you that only 14 out of 16 are correct. So you need to go back. Oh, I didn't put these together. Okay, let's try now. And it will tell you they're all sorted correctly. So I want you to try to make sure you've got them all right, and then go on to the next one. If you get desperate, you may graph things on Desmos if you can't get them right there. And then so it'll have the next one. You've got to match these here. And then you continue on. So you guys get the idea for that. So that'll be your assignment. I think there's 4. 4, yeah. And so the first 2 really you can do just by looking at the shapes of the functions. The next, like, here, you're going to have tables that you got to look at, so you got to think about like what's happening in the table. You could plug numbers in to see there, and then the last one's going to be more like graphs of the same type of thing, where you've got to know the difference between.